Hello, this is Chapter 18, More Applications in Optimization. And these are our learning objectives. Formulate and solve an integer programming problem. Apply optimization techniques to business and non-business problems. Formulate and solve a nonlinear programming problem. Introductory case, Northstar Biotech, the pharmaceutical project decision. Northstar Biotech, a multinational pharmaceutical company, is exploring 6 new vaccine development projects over the next 5-year period. Gordon Liu, the chief financial officer at Northstar Biotech, is responsible for determining which of the 6 projects the company should fund. Even though each vaccine development project is net positive, the company cannot fund all 6 projects because of financial constraints. The amount of cash available to Northstar Biotech is $10 million in year 1, $8 million in year 2, $7 million in year 3, $5 million in year 4, and $3 million in year 5. Gordon would like to use the above information to, number 1, develop an integer programming model to determine which of the 6 projects should be funded so that the total net present value of the capital budgeting projects is maximized, and 2, evaluate the impact of the funding decisions on the amount of excess cash available each year. Optimization with integer programming. Linear programming, LP, finds an optimal solution for the decision variables that can take on fractional values. In some applications, it is critical that the decision variables are integers. Include an additional constraint to the LP formulation that requires decision variables to be integer. Integer programming is a linear optimization technique that provides integer solutions for the decision variables. The process for IP modeling is similar to LP. 4 components: objective function, decision variables, constraints, and lastly, parameters. Include a constraint that requires the decision variables to be integer. Software applications can force an integer solution. Do not include a sensitivity analysis, and it's difficult to compute the range of feasibility, shadow price, and range of optimality. Rounding to integer values may give a suboptimal solution or an infeasible solution. If the coefficients are small and the decision variables are large, rounding may not have a significant impact. Example: recall the introductory case from Chapter 17. Yerba Buena Tea receives orders for 5,500 ounces of the chai powder mix and 4,000 ounces of the tea concentrate. An older production facility costs $190 per hour to operate and can produce 295 ounces of the powder mix and 260 ounces of the tea concentrate per hour. Because of its age, the old facility cannot operate longer than 8 consecutive hours at a time. A new facility costs $260 per hour to operate and produces 385 ounces of the powder mix and 375 ounces of the tea concentrate per hour. A single-purpose facility costs $150 per hour to operate and produces 350 ounces of the powder mix per hour. Modify the LP model into an IP formulation. Example continued. You have X 1, 2, and 3 represent the number of hours to operate the 3 facilities. Minimize production costs and the constraints: orders for power mix, orders for tea concentrate, old facility operating hours, non-negativity, and integer constraints. Here it is worked out with the worksheet. We plug in all of our parameters here using Excel, using R, other applications of linear and integer programming. Linear and integer programming techniques can be used to solve many real-world problems. We discuss 5 of the most common applications of linear and integer programming. Number 1, capital budgeting for selection of investment projects. Number 2, A transportation problem for selection of supply locations for product delivery. 3. An assignment problem where employees are assigned to specific tasks. 4. Workforce scheduling, where a manager establishes the schedule of workers to meet the demands. And W, facility location problem, where a decision maker determines the optimal placement of new facilities. In a typical capital budgeting problem, a decision maker tries to choose from a number of potential projects. These situations are often referred to as go versus no-go decision. It does not make sense to partially fund individual projects. The set of decision variables that are limited to only an integer value of 0 or 1. These decision variables are often called binary decision variables, where a positive decision is represented by the value 1 and 0 otherwise. Example, recall the introductory case. Gordon Liu, a CFO of North Star Biotech, needs to determine which of the 6 pharmaceutical vaccine projects should receive the funding. His objective is to maximize the total net present value from the funded projects. Use the information provided in the introductory case to help Gordon formulate this problem into an IP model. Example continued. And XI are the go versus no-go decisions for the 6 projects. CI are the net present values, or NPV, from the investment. And AIJ are annual cash investments in project I in year J. So, example continued in Excel. Make sure the solver add-in is activated. We plug in the parameters. Example with R. Transportation problems are solved with special LP and IP models. Objective, minimize costs for transporting goods from a set of sources to a set of destinations. Subject the demand and supply constraints. A set of constraints that the product ships satisfy the demand and do not exceed the supply limit. If the demand and supply both have integer values, the transportation model usually produces an integer solution. The transportation model deals with distributing goods or products contained in packages or large bundles. Example, Rainier Spring Water has 2 warehouses that service 3 retail stores. Every week, the first warehouse can supply up to 160 pallets of bottled water, and the second warehouse can supply up to 155 pallets. The manager at Rainier Spring Water receives a weekly order from the 3 retail stores for $85, $125, and $100 respectively. The shipping cost for each pallet varies among the warehouse and retail stores depending on the distance, traffic, and road conditions. Develop an integer programming model to help the manager decide how many pallets of bottled water to ship from each warehouse to individual stores to fulfill the orders while minimizing the total shipping cost. Example continued. Xij are the decision variables for the number of pallets to be shipped from warehouse I to retail J. Cij are the costs for shipping from warehouse I to retail store J. Example with Excel. And then with R. One common application in optimization involves a manager assigning employees or team members to individual tasks or roles. This application is relevant to a wide range of real-life situations such as in healthcare, education, project management, and sports. An assignment problem may be formulated as a maximization or minimization problem. The decision variables in an assignment problem are usually defined as binary variables. Example, a fitness studio offers 4 group exercise classes: yoga, stationary cycling, weightlifting, and high-intensity cardio training. There are 4 professional trainers who are certified to teach the 4 classes. The fitness studio regularly conducts a survey where gym members evaluate the classes taught by the 4 trainers. The studio manager wants to assign the trainers to teach appropriate classes in order to maximize the overall class evaluation. Formulate an IP model to find the optimal class assignments. Examples continued. X sub I and J are the decision variables in instructor I being assigned to class J.
Wij are the evaluation scores of instructor I teaching for class J. Maximize evaluation score. Constraints. Each instructor teaches only one class. Here is the solution with Excel. And then with R. Many organizations have to schedule their workforce while meeting the minimum demand for goods and services. Have a direct impact on the financial resources, productivity, and efficiency of the organization. Hiring too many employees may lead to idle time and wasted financial resources. Scheduling an inadequate number of staff could result in unmet demand, dissatisfied customers, and work overloads. A scheduling problem often has multiple optimal solutions that achieve the same value of the objective function. Having multiple optimal solutions in a scheduling problem may be useful as they allow the decision maker to choose from multiple staffing schedules. Example, a telecommunications company plans to open a call center to provide phone support for its customers. The call center needs to operate 7 days a week to serve the customers seeking help with technical and billing problems. The company needs to determine the number of employees needed to meet the daily demand. The number of employees needed to handle the phone calls varies each day. We can see the schedule worked out here and then all the different employees for the different days. So it looks like Wednesday and Thursday are the company's busiest days. Example continued. All employees are contracted to work for 5 consecutive days, followed by 2 days off. However, the company can ask individual employees to start their 5-day schedule on any day of the week. Use the provided information to formulate and solve the employee scheduling problem to determine the minimum number of employees needed to be hired for the new call center. Example continued. X prime I is the number of employees that start working on day I. Minimize the total number of employees. Here are the constraints. Here is it solved in Excel. And then R. One of the earliest applications of the optimization technique involves selecting suitable locations, emergency shelters, distribution centers, and medical facilities, meeting demand and requirements for all constituents. There's a long history and many interdisciplinary applications, numerous variations, but are collectively referred to as facility location or location problems. A facility location problem usually seeks to minimize the number of facilities and therefore the total cost, while satisfying the needs of all constituents. Example, a public health department needs to set up vaccine clinics to serve the residents of 6 rural towns. With its limited budget, the health department cannot set up a vaccination site in every town and must minimize the number of vaccine clinics. The public health department wants to make sure that the travel time from any given town to a vaccination site is no more than 30 minutes. Formulate the location problem to determine where the health department should set up the location. Example continued. Excel, and then here's R with the IPSolve package. Okay, optimization with nonlinear programming. Many real-world cases are nonlinear in nature. Variables and the objective functions or constraints have nonlinear relationships. Nonlinear programming is a technique for solving an optimization problem where the variables in the objective function or constraints have no or nonlinear relationships. Finding an optimal solution to an NLP model is usually more difficult than in an NLP model. The optimal solution to an NLP problem can be found anywhere. Nonlinear functions are also more difficult to model as they can take on many forms and structures. Obtain the best solution that is as good or better than all other solutions. Overall, optimal solution is referred to as the global optimum. An NLP algorithm does not always produce the global optimum. Many NLP algorithms yield a solution that is optimal only within a limited range of the decision variables. Better solutions may exist in another range of the decision variables.
The global optimum may exist elsewhere beyond the local optimum's immediate neighborhood. Optimization with nonlinear programming. Most software apps implement two types of NLP algorithms, derivative-based and derivative-free methods. Derivative-based, also called gradient-based, methods usually require that the nonlinear functions have a derivative or are differentiable. Do not work well with a problem where nonlinear functions are not continuous or smooth. You start by finding a random, feasible solution and repeatedly search for a better solution until an improvement cannot be found within the next few iterations. Relatively fast, but cannot guarantee a global optimum. Derivative-free methods, also known as gradient-free methods, can solve an NLP problem whose objective functions or constraints are not differentiable or not smooth. Continuous objective functions or constraints are too complex to find a derivative. Cannot guarantee a global optimum, but will generally yield a very good or near optimal solution. Compared to the derivative-based methods, derivative-free algorithms tend to be inefficient and often require the user to specify a boundary on the feasibility region. As in the case of LP and IP models, an NLP problem can be either a maximization problem or a minimization problem. Example, Beantown Gourmet Coffee produces regular and decaffeinated ground coffees and sells them to local coffee shops. The company has a machine for roasting and grinding the coffee beans to produce both types of ground coffee. Fearing a rising demand, the manager wants to increase the weekly ground coffee production. Recently, Beantown Gourmet Coffee has been operating near its capacity, but the manager believes that the machine can still operate for up to 50 additional hours per week. 2 new employees have been trained to operate the machine and can work up to 80 hours per week. Example continued. To produce 1 pound of regular ground coffee, it takes 1.5 hours of the machine time and 2.5 hours for the employee to operate the machine. To produce 1 pound of decaf coffee, it takes 1 hour of the machine and 3 hours of labor. Let X sub 1 and X sub 2 represent the additional amount of regular ground coffee and additional amount of decaf ground coffee. Because the company has been operating near its capacity, the profit for each additional pound of the regular ground coffee is estimated at 9 minus 0.21 X sub 1. The profit for each additional pound of the decaf ground is estimated at 11 minus 18 X sub 2. Formulate an NLP model to help Beantown Gourmet Coffee decide how many additional pounds of regular and decaf coffee to produce each week in order to maximize the total profit. An example here, X sub 1 and X sub 2 represent the additional amount of regular ground coffee and additional amount of decaf ground coffee. To maximize, you maximize the profit, 9 times X sub 1 minus 0.21 X prime 1 and squared. Constraints, employee time, machine time, none, negativity. Here's the solution with Excel. Here's the solution with Excel. Okay, I thank you for listening.